Saturday morning wasn't fine.
So does it get warmer or colder during the day in your home country? Maybe it's different there.
Warmer.
It gets warmer?
No, see, the hottest it gets today is 14.
That's nice.
Right now it's 11. Doesn't feel like 11.
What's it feel like to you? Because to me it feels warmer than 11.
Yeah, because we're indoors.
Yes. Not even outside. Anyways, Coulombs law next.
Yeah.
3 lessons left.
And then what's the next topic?
Then the final chapter.
Yeah, what's that?
Atoms.
Atom? Photoelectric effect of those.
It is nice, and it's not difficult. Bit of alpha, beta, gamma, decay constant.
Yeah, half-life.
Half-lives.
It is. It's a nice chapter to finish on. Most students don't like to do fields in the exam. I can understand why, but I don't think it's as hard as they think it is. It's just a bit confusing. No, it's possible. Yeah, no, we shouldn't discount this possibility. I would hope not, but maybe. Coulombs law. Please, I'm so tired. I went to bed at the time Fuang woke up. Went to bed at 3 o'clock. I was programming like a geek until then. Please. But just like this guy, I have to be up at 6 o'clock to get my train. The best of 2 worlds, exactly.
When you have a car, why do you...
You can't sleep in a car on your way to work. Well, you can, but it's not recommended.
Yeah, and then meant you are stopping and end up in a different city.
Fortunately, the train stops in the city centre, so I don't have to worry about ending up in Belfast or something. Alright, Coulomb's law. So, you remember that point charges produce an electric field. Let's look at the force of attraction or repulsion between these. So does anybody remember the formula here? You have, let's say, a charge here Q1 and a charge here Q2, and we'll say it's attraction. So whatever, this could be positive, this could be negative. So what's the formula for the force? Does anybody remember?
QV?
Almost.
It has a V?
Q1, Q2.
No V in this one.
Q1 minus Q2.
I forget what we did at the start.
Just Q2.
No.
Q1. V1. M1.
Let me help you out here. There's a field around this.
E?
Yeah, E.
Or QED? QE, yeah.
No. That's for the parallel plates,
Q1,
not for the
E,
point.
Q2,
That's QE.
Yeah, QE.
Why did you do that?
I apologise. It's not Q1E. It's Q2E because this is the one that's moving. But the E is caused by Q1. Now, does anyone remember the formula for the electric field strength around a point? The one for the parallel plates was V over D, and we had one for the... No? If you recall, the E was K.
Is it F over Q?
KQ1 over R squared.
Close.
Guys, we did this at the start of the chapter, so...
Wait, what was the E is equal to F over Q?
Oh, yeah.
That's this formula here.
Oh. Yeah.
Right, so this becomes KQ1 over R squared, or in other words, K Q1 Q2 over R squared. That's the force between 1 and 2. It can also be written as 1 over 4 pi epsilon 0, which is on your calculator, Q1 Q2 over R squared. This is just a different way to write this constant. It's not really important for our studies. But the value of it, I believe, was 8.99 times 10 to the 9, if I remember. And we talked about this at the start of the chapter. I guess that was too long ago now. Must have been, what, 2 weeks ago?
Or we relied on its being in the point level.
Yeah, that's a bad thing if you do it too much. So this is actually Coulomb's law. This is the force between two charges. Now what's not clear here is the direction, because it depends on the sign. So at the very least it's just the magnitude of the force. But I would hope that in your high school physics class you've seen this formula before.
That's even older than 2 weeks ago.
Yes. Yes. And do you remember it? This formula?
We don't remember what we did 2 weeks ago.
So good luck with that.
F1, 2.
The force between 1 and 2.
And then, what's the one?
I'm just saying that I'm not telling you the direction because it depends on if they're pluses or minus.
What's the constant number on the calculator for K?
I don't have my calculator. What's will tell. No, K is not on the calculator. Only the 4 pi epsilon 0 is.
So we'll have to 1 over the cost.
Yeah, but K is in the formula book in the exam.
Yeah, but when we're calculating, we'll use the calculator, so we'll use the...
Yeah, and the calculator has numbers on it, and you can type the value of it in using the digits. Yeah, yeah.
Okay. But this means we'll have to memorize the number.
No, because you're not listening to me, Faisal. I said 10 seconds ago, it's in the formula book.
Oh, nice!
More coffee is required. Right. Can I continue? Okay. Whoops. So, I have Coulomb's law now. We just wrote it down. And we know the usual story here with Q1, Q2. By the way, the units for K, we proved this earlier in the chapter, is newtons per Newton meter squared per Coulomb squared. Now let's have a look at how Coulomb's law works here.
Sorry,
Yeah.
what unit?
Huh?
What
Oh,
unit
yeah.
is
The unit. There it is there. For K.
It's in the formula.
It is actually, yeah. Yeah.
Force is just newtons.
Yeah, but the K. The units for the K.
Oh.
I mean, if you think about it, it has to be this because the meter squared has to cancel the meter squared, and the Coulomb squared has to cancel the Coulomb squared. You'd be left with newtons because of the force. So it makes sense. It's like physics makes sense. Okay. Continue. Yeah. Okay. Now, where's the force in this picture?
Electron to proton.
Yeah, so if I was to draw the arrow, the force vector, where would I put it? Where would I point it?
Towards the proton.
No.
Where would I put it, and where would I point it? So you've only
inside the atom.
Where? Here?
Between them.
Can you just... Okay, you be quiet now. Go ahead, go on. No, please, don't let Faisal talk all the time. Give me an answer.
And she said anything similar to one.
From electron
Yes?
to the proton.
Thank you. Thank you.
No.
No.
I said between them, from the electron to the
Between them
proton.
is anywhere
them, yeah.
here. Come on, your English is better than that. Yeah.
Okay. Never pronounce your word.
As Fu Wang was saying, you draw the force from the electron to the proton. But there's also a force from the proton to the electron. So in the picture, you have it like this. This is an atom. Right, so there's a force this way, F. And let's call this particle number 1, and this is particle number 2, and this is the force between 1 and 2. And let's say there's a force this way, and this is the force between 2 and 1. What is the relationship between these two forces?
Equal.
They're equal. And they're equal because if you think about the formula,
What does Newton say?
well, it's actually Coulomb. And if they're equal because it doesn't actually matter about the order of the charges, the total is the same. So, if these forces are the same, why don't they move towards each other? Or rather, I should say, why is it that the electron is orbiting the proton?
The mass.
It's because the mass. And this is something we discussed earlier in the chapter as well, which we already explained. So, often we ignore the proton for a picture like this because, true, the proton is moving slightly towards the electron. Really, all the action is with the electron. That's right, the electron gets all the action, and the proton gets very little action. Okay. When one charge Q is trapped by another charge big Q. Now the reason I wrote small q and big Q is on purpose because I want you to picture something small around something big. What type of potential energy will it have? What do we know about the potential energy if it's trapped in an orbit?
It's negative.
It's negative, yeah. Because it's trapped. It has negative potential energy. And in fact, if you wanted to work out how much potential energy it has, it's this formula.
You only remove the square.
Yes, that's all. Interestingly, you only remove the square.
For the force here, why don't we just write the formula as q squared over r squared?
These are different.
Yeah, but we just said that they are equal.
The force is equal. The charges are
Oh,
different.
okay, yeah.
Okay, did you write
This is the potential energy of the small q.
correct, yes. Because the big Q is stationary.
What if the big q is stationary? That means that it has potential energy because the small one is moving. It should
Why would that have potential energy?
The stationary.
But why does being stationary make that potential energy?
Doesn't stationary potential and moving kinetic?
No. Kinetic is moving.
Yeah.
Potential has nothing to do with being stationary. Potential just has to do with what could cause it to suddenly move, like gravity. Continue. Yeah.
What's the big Q?
It's just a charge.
Of like what's the the charge? They're both charges.
Yeah. I'm trying to emphasize the fact that the small q is around the big Q. It doesn't matter. You can call it Q1, Q2.
Small q is the electron's charge.
Yeah, like the small q is like the electron, and the big Q could be like the atom or something. Yeah. Okay, continue. Yeah. Coulomb's law gives the size of the force between the two charges. This force is one of the four forces of nature. I wonder, does anybody know the four forces? So the first force is due to Coulomb. Yeah, Coulomb's force. The second one, as you said, Yusuf, is due to Newton, which is gravity. So these are two of the four basic forces of nature. Does anyone know the other two?
Light intensity? Heat?
Heat is not a force.
Yeah.
We don't measure heat in newtons. You know, oh man, it's like 96 newtons outside. It's killing me.
No, I was thinking base units.
Yeah, force. Basic forces of nature.
the gravity of the moon and the tidal wave. The force.
Oh my goodness, the next time you demonstrate that you're not listening, I will stop you. I
What?
just said
Yeah.
we have Newton and we have Coulomb, gravity and the charge. Okay, what are the other two?
Like a force applied by someone. Like if you move
Of nature.
Bubble bubble.
Huh? Okay.
My mom and dad.
Is it like wind and
No. No. More, by fundamental we mean like present at the atomic level, basic forces of nature. So, I just wondering if anyone did them at high school, huh?
magnetic field?
Magnetic actually gets grouped in with Coulomb. So we have electromagnetic, which is Coulomb, and then we have gravity, which is from Newton. So the other two are called the strong and the weak nuclear force, which we'll do later in the chapter. But what's interesting is Coulomb's law is an example of an inverse square law, and these laws are surprisingly common in physics. And it's worth examining why that is. So, inverse square law, what I mean is this. In the formula, in the bottom, there's a square. And it's in the bottom. In physics, you'll see this formula a lot. You'll have a thing, I'll just write thing, equals some other thing over a distance squared. This is a really common formula in physics. And what is the reason why? So I'll give you a very sort of silly example to demonstrate the reason why. And even in my silly example, we'll see we have this formula here. Okay, so let's look at what happens, right? So let's imagine I want to measure something like how smelly a student is. So we want to know how bad they smell. And we'll measure the unit, I don't know, we'll call it stink units. Smelly units, SUs. Yeah? Or whatever unit you want to imagine. You know. Call it the, I don't know. Who's not here? Wong. We can call it the Wong unit, if we like. Whatever. So, here is our student. And here is their stinks. And we are standing here, and we measure their stinks on the, what would you measure their stinks with, by the way? Stinkometer, yes, stinkometer, obviously. So, if you think about it, as we increase our distance, the amount of stink units we have, it stays the same, but it's being spread out over a bigger area. So let's imagine here this is 2 stink units. Here this is 2 stink units, but this could be 2 stink units over, let's say, 3 meters squared, whereas on this one it could be over 4 meters squared, and this one here it could be over 5 meters squared. That this area is getting bigger, but the stink level is just getting spread out over a bigger sphere, a bigger ball. The area here, the formula is 4 pi r squared. But the stink coming from the student stays the same. So the stink density, that stinks per meter squared, that would be some constant, which in this case would be 2 stink units, over the area. Which will be a constant over 4 pi r squared, which will be a constant over r squared, the stinks. So, whenever we're in a situation in physics where something is expanding outwards, like Coulomb's force, often the formula is like this. The square is caused by the fact it's spread over area. And I just think it's interesting because a couple of the basic forces of nature have this particular form. which means that there's something kind of special about this. But when you realise, oh, maybe it's not that special, because all that's happening is the thing we're interested in is being spread out over a greater area as we sort of move outwards. This is not on the exam. I just thought this was an interesting side note for explaining why this formula is common in physics. Also, later we'll talk more about why the value of k is so large. Do you remember what the value of k is?
8.99% to the power of 9.
Yeah, 10 to the power of 9. And that's actually an extremely large constant. And that's actually worth talking about later in the chapter. Okay, so here's a small question for us to try. I'd like you to try it for me. What is the force between a proton and an electron? And they're 0.1 of a nanometer apart. You can use your calculators directly here. The constant is 8.99 10 to the 9. Faisal, where's your calculator? No, seriously, where is your calculator? How many weeks left until I'm not teaching you? I mean, how many weeks left until the exam? Not that I'm looking forward to it. What? 2 weeks?
Yeah.
Include-
After this week.
After this week, 2 more weeks?
Yeah.
You need to make sure
Awesome.
that we pass, so that we don't come back next week again.
You see, that's one come with you.
No, yeah, hey, no, it's only certain individuals I don't want to see again.
Oh no, you don't want to see anyone.
Like you?
I'll come with you.
Charge of proton and charge of electron.
It's the E.
The R is radius.
That's the charge of a proton.
It's also E.
It's the same.
Oh, right.
Oh, 3.5 times 10 power negative 51.
51?
51.
That's outrageously small.
2.3 times 10 to the minus 8.
That's more reasonable.
K times
What's K?
E squared.
What's K? Did you type K in on the calculator?
I think it's
No, it's constant 25.
K is constant 25.
No.
Lee,
Oh, yeah.
Lee, can you just hit Faisal around the back of the head, please? Just right here. Go ahead, it's okay.
2.3.
No, hit him, not
Times
stroke
10 to
him.
the minus 8.
Faisal!
Times 10 to the minus 8.
Faisal!
Yes, I'll write that.
I told you that K is not on the calculator, it's
No,
in
you
the front.
didn't.
What's the second charge?
It's the same. It's mostly.
Please, Lee, please. I told you K is not on the calculator, it's in the formula book. 8.99 times 10 to the 9. And you would have to type it in. I'm getting worked up.
If you really want the accurate value, just type in 4 pi times constant 20.
Oh.
But I told
You want to use the calculator.
What is that?
2.3 times.
What constant number is epsilon 0?
Use
Use
T2.
Okay.
22, yeah.
right.
What unit for the ratio of proton?
Oh, and it will be
What do you mean meters?
Meters.
Oh,
Nanometers, like times 10 to the minus 9.
Oh. Couldn't square the bottom.
Oh, no. That's stupid.
Is it? Oh, because it's nano.
Yes.
Minus 9, yeah.
Duh. 2.31. Okay, so let's just put this in 23 nanonewtons. 23 nanonewtons. Yeah, cool.
No.
Cool. You're cool.
No. I'm not.
What's wrong?
Can you do it with 8.99?
Yes.
It's not just 8.99.
You did put in times 10 to the 9, didn't you?
No, it's 9, power 9.
Yeah,
8.99
you
power
did.
9.
Okay. 8
99
yeah,
power 9. Yes,
same answer.
that is what I wrote.
No, it's not.
Yeah. E squared.
Yeah.
I wrote E times E.
Yeah, okay, fine.
Over 0.1
Yeah.
times 10 power negative 9.
Yeah.
That bottom is square.
Yeah.
Times 8.99 power 9.
Now, are you using that stupid 10 button I don't like? Because this happened last time as well. You know that button I'm talking about, the 10x button, or whatever it is? I hate that button. It doesn't work properly. Is that the button you use, Faisal? Is it?
No.
Look at me! I'm continuing now. And that 10x button is forbidden in this class, alright? What's the word? Haram, is it? Haram, yeah. Excuse my pronunciation. Alright. Only the 10 power button is halal, alright? Okay.
Still not getting it.
What? Show me, pass the calculator over, I want to see what you typed in. Pass the calculator, no, not you, I don't want you over here, I want the calculator. Now sit back down. Sit
No,
back
I
down.
want to see.
Sit back down. Look at what he typed and tell him what's wrong.
It's 8.99 times to the power of 9. You're supposed to times 10 to the power of 9.
Nice! See, that's how I use the extent.
Goodness. This pain, it's painful. Some things are just painful.
Use the 1/4 pi.
Right.
It's more convenient for you.
Here is a harder one now, but we did one like it. How long does it take an electron to orbit a proton when the orbit's radius is 0.2 of a nanometer? This could be like a section A question for 5 marks in the exam. Which is nice, it's 5 marks, but you know, there's a couple of steps to it. So you have to think about it. I'll give you a minute here.
I remember I answered this question from my first paper and there was a formula and now I don't remember.
Yeah, that's life, huh?
This thing here. Was it four
Let's see.
squared? Or was it It's like one of the formulas for this thing. For this last one. Is it this one?
I don't think that's quite the formula. You want the? I'll give you a little hint. You want a little hint? Remember the formula for the force caused by circular motion. F equals m omega squared or. Yeah.
That's it?
Well, no, that should help you along the way.
What's omega then?
Sigh.
I can't remember the formula.
Omega is
Yes?
beta over T.
Yeah, but that's not the helpful one here.
V over R. Not helpful.
No, not helpful either.
Martin.
If there's a,
T
that's the
equals
one.
2 pi over omega.
And what are you looking for?
T.
Yeah, well, omega then T if you want.
Yeah. How to find omega?
Well, can you find the F?
Yes.
Do you know the OR?
Frequency.
Do you know the OR?
Yes.
Do you know the F?
Yes.
Yes.
If you have the R,
Yes.
find that.
Yes. You know the F and the OR. And the M, can you know the omega? Yes. Now it all falls into place. Faisal, stop touching yourself, please, and do the question.
Can you tell us what omega squared is?
It's equal to omega times omega.
No, like the the omega, like omega is the
Yeah, omega is T is 2 pi over omega. Okay. Yeah?
One more minute.
Okay. Huh? What's
What do you
wrong?
want? What do you want?
I got some formula.
Which one? For T?
Omega.
Aye. So we have these formulas. And you have this one.
It's a small number.
And then you have this one. No, what am I saying? Sorry. T. So, if you use this, you can know this. You also know this and this, so you can find this. If you know this, then now you have your answer. Got an answer?
Yes.
Awesome.
Yes, this is small.
Is it? Oh yeah, because the electron is flying around the proton. So what answer did you get?
1.12 times 10 to the power negative 15.
Small. Smaller than I thought, but no, I think that's right. Because it's quite close to the proton, and the closer it is, the faster it'll go around. What time did you get? Okay, I'm lazy and I don't want to type it on my calculator. So for me, mentally, it's easier to get the formula and then just put all the numbers in at the end.
I got 10 minus 5.
No, that's too big. Well, let's have a look. So you know from here that omega is the square root of f over m/r. True? But you can know the f from Mr. Coulomb. He said it's k q1 q2 over r squared, and this is still over m/r. So this will be square root k q1 q2 m/r over r squared. What cancels here?
Square on top.
Yeah. So you can say that t is 2 pi over omega, so that's 2 pi root r over k m q1 q2. So as I promised, I'm lazy and I want to type things in my calculator just once. So the answer will be 2 pi root, what did I say the radius was? 0.1 or 0.2 nanos? 0.2 nanos or 2 nanos? 0.2. Right, and now what constant number is, oh yeah, which mass is that? The proton or the electron?
Electron.
Very good, yeah. And what constant is that on the calculator? Is that 3, is it? No, mass.
Like 3.
3. Okay, and then the charge is E, so that's E squared. What was your answer?
Times 10 to the negative 15. Done.
Dang. But I'm wrong. I'm totally wrong. because my answer is
Yeah.
completely ridiculous.
2 pi isn't, I think.
I have a question.
No, wait. What went wrong?
I think it's 2 pi.
You're over. 2 pi
Why
over.
did you?
Yeah, 2 pi over.
No. Yeah, but I flipped this upside down
Yeah, why did you flip this upside down?
because it's divided. So what did I do wrong? Ah! Wait, did I get my nano right? No, I did get my nano right.
You're okay.
My K is right, isn't it?
Yeah.
And this is
You did
electron.
ME and then E square.
Yeah, mass of electron times charge times charge. Hang on, let me just make sure I'm not doing something stupid here. This is omega. F over m or square root. True or false? True. And omega, this is F. True. Over this. Which is this. And T is 2 pi over omega, which is this. No. What went wrong?
Why did you put the M on?
Huh?
Wait, where's the S?
Oh, wait! No. What?
Oh no, S.
This is a mystery now. My answer's totally wrong. Why is it totally wrong? Everybody was watching me do this and nobody saw me making the mistake, even Lee. So what?
I think it's in the second line.
Wait, are you?
Yeah, what do you think?
I'm so happy you got it.
Now hang on, his answer could be wrong
I
too.
could be wrong.
Yeah.
Oh.
Okay.
I'm curious now.
Just don't flip the thing. That's
No, that's
it's R cubed.
or cubed. No, it's not.
Yeah, by the way,
That's R.
Yeah. This or.
This. It's wrong.
Yeah.
Oh, here's wrong. Thank you. Yeah, this doesn't go on the top.
Yeah.
This goes on the bottom. That should have been down here. Yes, thank you. So you're right. Instead, that should be 2 pi root m or cubed over k q1 q2. Maybe it would have been easier if I got the numbers along the way instead of trying to do everything at the end. I learned a valuable lesson, but I'll forget it next time. Right, let's recalculate. So, I still need k and this on the bottom, but this should be, this is cubed now,
And there is an M.
and there is an m.
No.
Yeah.
That's not the R. No, that's not. Okay.
Dude. Right. Okay, this is Andrew's moment of truth now.
Yes.
Awesome.
You're an answer.
1.12 times 10 to the minus 15 seconds. Good job, Andrew. Okay, can you write that down if you didn't get it? Continue? continue? Okay.
Got the whole bag.
Here's a very short question for you to try. What potential energy does an electron have if it's 0.15 nanometers away from a proton? Do you have an answer, you see?
1.7 times 10 power negative 18.
Wrong.
1.5.
Nearly.
Everything's right except the 1.5.
Yeah, but crucially, don't forget the minus. Yeah. So, the formula is minus
Could I just look at the distance really quick?
K Q1 Q2
I did 9.88.
0.15 times 10 to the power of minus 9. That is the potential energy there. That's what you got, isn't it?
But you said that Q1 and Q2 are different.
Yes, of course they're different, except when they're the same. Yeah,
Electrons and protons are the same.
yeah. People are different, correct?
Yeah.
Except when they're the same, i.e. twins.
Yeah, same but different.
Same bubble.
The only difference between them is the sign,
Yeah. Yeah.
So why do we not take that into consideration here?
Yeah, I'm being a bit sloppy with my signs, but it's potential energy that's trapped, so I have to make sure it's negative. So really, if you want to be technical about it, there should be an absolute in the formula, that you only care about the size of the number, because the sign is automatically a minus. Yeah.
The question is like the distance.
Mm-hmm.
The O.
The distance from the proton to the electron, yeah. Yeah.
But if you use like for Q1 and Q2, one is positive and one is negative, then
As I
you
was
get a
saying,
positive.
to Andrew, I was quite sloppy with my signs. If you want to be technical about it, the formula is really this.
And Q1 and Q2 are positive both.
No, it doesn't matter, because the absolute,
Oh, okay.
if you're going to be all ganging up on me with the signs, it's going to be like
No,
this
just,
then.
We're done.
Now, hang on, you do have a point with the signs, because this is if it's trapped.
If it's orbiting.
If it's in orbit. But, and that's the only time I use this potential energy formula. But I suppose technically, if you have a situation like this isn't in an orbit. This will want to move away. So in that case, the potential energy is actually positive. So if it's not in an orbit, then it would be like this. But I mean, you never use potential energy formula in this situation, because for atoms you always want to know this problem. What is the energy of the trapped electron? Because in chemistry you need to know things like ionization energy. How much energy is required to free it? By the way, how much energy is required to free it? That's how much potential energy it has in the negative.
Sorry, could you repeat that?
Yeah. Ionization energy is actually just the negative potential energy. Because if I said this had minus 1 nanojoule of potential energy, that means 1 nanojoule of energy is required to free it. i.e. the ionization energy. Yeah? Okay.
Just minus 1.5 times something minus 8.
Here are 4 short questions I'd like you to do, please.
Now?
Yeah, now.
No.
We have class.
Yeah.
That was a double class.
No.
No.
Yeah, chemistry exam.
Yeah.
Are you sure?
We have it in a minute.
Do we normally have a double now?
No.
Never.
Yes, it is.
Yes, yes.
We have
The chemistry
even,
is.
then even. That's not the same.
You know what must have happened? When I looked at the timetable, I saw Stephen, great, I have him for 2 hours. I didn't bother to look after Stephen. Stephen B. Oh, that's not me. Right, so what room are you in?
Just
D213.
Jinx.
Get going. Go. You don't want to be late for the rain. Go.
Okay. Should be late.
We only have 40 minutes.
There's no key.
Our student.